until the first test, we were really talking about fluid statics. So none of the stuff that's involved in here will be included in that, but this is ultimately the goal of what we'd like to be able to say something about is moving fluids. Actually, you can say something about this. If, for instance, you wanted to calculate the fluid pressures as you go down the waterfall in that tail of water, you'd have enough information to be able to do that. We have this expression of dP dz is equal to minus the unit weight of the fluid, and that's true for statics, but of course this is moving water. There's an extra term that's added to that, which is another acceleration term, and of course the water, as you drop it, just as you drop a ball, will be accelerating due to gravity. And so if you wanted to, you could go back to that one expression we have, and you'd find out that the pressure gradient with depth as you go down a waterfall before it hits the bottom would be exactly zero. It's weightless, just as you'd feel weightless if you're falling through the atmosphere. So this is probably not so related to what we're talking about now. We're getting ahead of ourselves a little bit, but kind of inspiring. It's what we should all be doing, right, this morning, instead of sitting in here maybe. If you're thinking about what you'd like to do in terms of presentations, which we haven't yet ascribed, we'll assign groups next week probably, when all people have migrated to the class. Those who've dropped it have dropped it. So groups that we have will be groups throughout the whole semester is the basic rationale of that. You might think about some interesting and, I'd say, enigmatic or mysterious fluid mechanics topics, of which this is one, I guess, trying to figure out how to open a shaken up can of soda as a function of what happens. And so I don't know whether they will do it here. I mean, basically the idea is that the suggestion is that all the gas is nucleated on the side of the container once you shake it up. And by tapping it, instead of allowing it to suddenly, as you release the pressure, so there's some pressure in this container. The container's pressurized, as you can see by the teat on the top. And the nucleated bubbles are on the side. And so the idea is that if you open it up now, those bubbles are at pressure. You release the pressure from the headspace. All of a sudden they expand according to the ideal gas law, and they push the water up with them. But if you take those bubbles off the side first and move them up to the headspace, then there are no bubbles to expand. So I think it's kind of a curious... so those are the kinds of things that you might think about. There's some a little more raucous ones. Of course, this one that we'll show now is... we won't do free diving. Actually, I took it off. Well, you all know the trick where you have a glass bottle of soda, of course, and someone taps it on the top with another bottle. What happens? Pours out the top. Why is that? Does it happen, for instance, if you did it in a plastic bottle? I think it doesn't. I think what happens is that you bang a bottle on the top of a bottle. There's the acoustic wave goes down the glass. It hits the bottom of the bottle, bounces off, comes back as a tensile wave. It cavitates the fluid in there, and the fluid just comes up. So I think that's part of what goes on here. So I won't talk about free diving, but I will see if this comes down. So drilling holes in the ground
Build particles and transport them to the surface.
Petroleum products.
To cool and lubricate the bit and drill string.
I won't bore you with that. So drilling fluids. So you drill a hole in the ground. It's a long circular hole that's maybe 3,000 meters deep, 9,000 feet in Marcellus, for instance, here. You use drilling fluids to do perform a number of functions. One is to bring cuttings back to the surface, so it's actually moving. One is to actually push against the borehole to keep it open so it doesn't close and collapse on you, or the stuff doesn't slough off. And so to do that, it exactly follows the principles that we've talked about in this class, and that drilling fluid is a liquid. Sometimes it's drilled with foams or airs, which are compressible. More usually it's a liquid. And as you saw on this previous previous
In
slide,
such
the
cases,
pressure
the
change with
drilling
depth
fluid
is
will
just
be
this
weighted up with a high
triangular
speed gravity
distribution,
additive.
increasing in pressure
Typically,
as
the
you
column of
as you
drilling
go
fluid
down in
exerts a
depth.
slightly higher pressure than that within the.
So I'll leave that. Some of the other things that we were interested in understanding. We're interested in pressures at a point, because that's what we're talking about so far, and we'll continue talking about that today. But the next thing is to talk about pressures distributed over areas. And so distributed over areas could be the sides of a well bore, keeping the borehole open, and how that magnitude changes. Not so important for that, because we just need to know what the individual location, the pressure at a location is. But if you look at structures, for instance, dams, which have a static lake behind them, and you can now calculate what the fluid pressure is at the bottom of that lake. You could also calculate the total force due to this triangular distribution behind the dam. And so if the dam happened not to be completely well founded on its foundations, then it might not stay in place. And so certainly in that Malpasset Dam in the south of France in 1959, if you can read this, did exactly that. It was one of the first events of this kind, where you have a high dam, very thin skin made out of reinforced concrete with an arch to it, the arch pointing upstream, and the foundation moved, the dam cracked, and a surge wave moved down the valley, killing 400 or so people. And you can do simulations to be able to figure out exactly what the hazards of such a collapse would be. Of course, you'd like to design the dam that's strong enough to be able to resist the pressures that we will be able to next week calculate that are applied on that back surface. And so our interest in this is to be able to take what we've done on fluid pressures at a point and be able to apply that to calculate what magnitudes of the forces would be that would be applied on a structure, and to be able to say whether that structure moves or not. And so that's kind of our ultimate goal. So if you wondered where we were going with this, that's kind of where we're going. I'm going to stop there. Right. So, any questions so far from what we're doing? Everyone, I hope, has found the resources. I still get questions. Is this stuff online? I will reiterate. Perhaps I regret my statements that the book is only recommended, not required. If this stuff doesn't come absolutely naturally to you, you're probably worthwhile investing in the book because it covers all the material that we're talking about. And so for the cost of a book relative to your tuition, the ratio of those, I'd make the case that that's the ratio of those is small, even though it's an $80 book. Okay. All right. It did get larger. All right. So we're in the third class of the second week. Remember the things that we know. We know that fluid pressures at a point act the same in all directions. We know that if we go down in the fluid, absolutely pressures increase always with the unit weight of the fluid. That fluid can either be constant density as in a liquid, in which case we get a pressure distribution something like this, or this fluid can be a compressible fluid where the unit weight changes with the pressure, and in which case we end up with a slightly different expression, which we developed last time for the atmosphere, both at constant temperature and at changing temperature as you rise up in the atmosphere. So those are two of the three important rules. I guess the other one is that you move horizontally in a fluid, then the fluid pressure doesn't change, so long as it's the same fluid and you can get from one point to another without exiting it. So those were the key issues that we used to be able to define these manometer rules. So the manometer rules were for us to be able to figure out exactly how fluid pressures vary within static systems, and manometers are things that allow us to measure the pressures in systems. And so as a direct consequence of, I guess, this, is that if you go up in a fluid, you subtract a pressure, as you can see here, right? If you go up in a fluid, you subtract a pressure. If you go down in a fluid, you add a pressure. If you move across a fluid horizontally, the fluid pressure at two locations, if you can physically get there in that same fluid, have to be exactly the same. And if it's evacuated, then we should use the vapor pressure. And if it's gas-filled, then because gases have densities that are roughly 1,000th, certainly normal pressures that we work with, close to atmospheric pressures, they're about 1,000th of the density of liquids, we can completely ignore them. And so what I wanted to do today is just go through some examples, which are these few examples that are included here, and just work through them at our leisure to be able to just get used to it. But it will basically use these I guess this is one rule, this is two rules, I guess four rules. These four rules. Okay. So, can everyone see that? Should I make it slightly larger even? It's maybe too large. It's too large. All right, so some examples. Let's just walk our way through them. We have an upside down bucket that is put into water upside down. This upside down bucket has a hose that comes out of it, and in this hose is a gauge fluid. There's a headspace that's put here, and initially the bucket, when you put it into the water, of course, would rise with the water at this level. But then, so you put the bucket in the water, you put the gauge fluid into the tube, and then you pull the bucket up. When you pull the bucket up, then what it does is it pulls the water that originally was at this level up with it. And so we're left with a couple of questions here that we might like to figure out. One is, what is the air pressure here? Or you could ask also, what is the force that we have to apply to get to lift this thing up? Those are two questions we could ask. If we wanted to calculate what the air pressure is, then what we could do is we could write the behavior of this, actually not the air pressure. So the question is actually in this case, what is this height that's present on the manometer? Which is basically saying what is the differential on this? And of course this differential in pressure will actually be the air pressure that's in here. So how do we do that? Well, we realize first that we can get from this point. Realize first that we can get from this point here to this point here without going outside the fluid. They're on the same elevation, so this has to be equal to PB. It's sitting in atmosphere out here. This is just sitting in the atmosphere, so this has to be equal to atmospheric. 1, 2. And so what we could do is we could work our way through this as we did before. Bless you. So we start off with PB. We're going up to this point, so we should subtract off 2 feet multiplied by the unit weight of water. So that's the pressure to get here. This is in a gas, and so we don't care about the fact that this is. So the pressure here has to be the same pressure at this location here, because it's being applied by the gas. And then to get to this point here, we have to do what? We have to go down 3 feet, and we have to go up h feet. And so this would be going down. So we would add h minus 3 feet multiplied by the unit weight of the gauge fluid, and that would equal PB. Like we could call this PA, P atmospheric. And so we've gone up, we've gone down, which would be, so this is the wrong way around, this is a minus, I think. And we've ended up at this location here. So right, so we've gone up, so we've subtracted. From here, this has to be the same pressure as this. We've gone down, so we've added. We've gone up H, so we've subtracted, and we're left at this pressure here. And so we know that since we do things in atmospheric pressures, we can make this equal to 0. We can make this equal to 0 as well. And so all we have is that this expression here. There's only one unknown in this, which is the height, which we don't know. And if we rearrange it to get that, we end up with the height as being 2.2 feet. Okay? And so you notice that 2.2 feet, of course, is not there, but 2.2 feet would be here. And so we can figure out whether that makes sense in terms of what this would mean. This would mean if there's an excess pressure here, if we just go across here, then the pressure at this point here has to be this height of the gauge fluid. The height is positive because we have this gauge fluid on top of us, so it would be a positive pressure that we'd feel. Clearly, if this is a positive pressure, we can't imagine pulling this height of water or this weight of water up. And so if it's down here, it means that the pressure PA is less than atmospheric. It's less than atmospheric by 0.8 feet of water. And so that's the magnitude of the pressure. And so what we've got from this is directly the magnitude of the pressure at A, or actually we've got the height of this fluid. How do we calculate the force R that we could apply to pick this up? There's a couple of ways we could do it. Okay? We could imagine that we have this upturned bucket, which has air in it, which is this part here. And we have a force equal to the pressure at A acting downwards. And so the force acting downwards is going to be equal to the pressure at A multiplied by the total cross-sectional area of this bucket. So the area would be this area in here, right? This would be A. Sorry about the confusion with this point A, but this would be area. And the only thing acting upwards is going to be R. This thing. Imagining that everything else is weightless. So that's one way to do it. Is there another way to do it that you could think of doing it? No takers? So the other thing we could do is, if we realize that this is atmospheric here, and this is atmospheric here, we could just cut this bucket off at this point here and look at resolving the weights. We'd have this height here, which is 2 feet. The weight acting downwards is going to be equal to 2 feet times the unit weight of fluid times the area. Right? These two things together are just the volume. I'll move that up. This is just the volume between these two. 2 feet times an area is a volume, multiplied by unit weight is a force. So this is the weight of the water. You have a weight of gas, of air. Not written there very well. It's going to be trivial. It's going to be 1,000th of this, right? So we're not going to bother calculating it. And actually we don't know what that weight of air would be because we don't really know what this height is. And we have a force acting upwards, which is R. And so in the same way that in this case R is equal to F, in this particular case, the bottom case, R is equal to W. They both should be the same numbers. You can do the calculation. 2 ways to skin a cat, right? More than one way to skin a cat, as the expression goes. Not a very good expression, I guess, if you're a cat lover. And I think those are, yeah, so that's calculated down the bottom as well, right? Everyone okay? Right. All right. Differential. We talked last time about measuring differences in pressures between things. Sometimes if there's a big pressure and a slightly smaller big pressure, there's a small differential between them, but it's the differential that is important in, say, driving flow in a porous medium. So sometimes it's important to be able to measure differential pressures. One way to do those is to do it with what's referred to as a micro-manometer. And it's just a manometer, but the difference in the micro-manometer is that it's measuring a fluid pressure P1 and a fluid pressure P2 and the difference between them. But it comprises two fluids. It has a gauge fluid of some density, unit weight 2, and it has sitting on top of that some other supernatant fluid. And if the difference gamma 2 minus gamma 1 is small, not zero, but small, I guess, then it becomes quite sensitive. And it becomes quite sensitive because the pots that have this fluid in them have quite a large cross-sectional area. And so a small drop in this level here would give a large change in height. If you imagine putting a bead, for instance, in this tube and pushing this down by some small amount, then this bead would go down by a much larger amount because of the ratios of the diameters of the tube. And so if you imagine it being just a single fluid that has a bead in it, then this area here magnifies the distance that this will travel for a given pressure change, and you can measure that with much higher resolution. So that's the idea of this particular instrument. And so we can do the same thing to be able to show exactly how that would work. So we start off with a system. Apologize for the writing on this already. Let me do it in different color. So it starts off in an equilibrium condition when the fluid level here is here, and the fluid level here is here, and the fluid levels in each of these two components with this gauge fluid is on this horizontal plane. We add a fluid pressure here to change it so that this goes down some amount. If this goes down some amount, this one will go up some amount. And as a result of that, the fluid in this manometer will be displaced some amount down here and some amount up here, just by continuity, like a seesaw. This side goes down, the other side goes up. This will go down by the same amount as this goes up, but this will be magnified because of the cross-sectional areas of these things. So what we can do is we can write an expression which defines this behavior. And so we can start off in this configuration at this point here. This will be P1 when it's depressed. P1. We're going to go down to this point in this one fluid. So this height here will be H1 minus delta H. H1 minus delta H to get to this point. We're still going down in the same fluid. This will be plus H, should be this one here. And so now we're sitting at this point. We're in the same fluid. We can go across to this point here, and that'll be the same pressure that we've calculated up to this particular point. We're going up an amount which is equal to H in this second fluid, which is this amount here. We're going up another amount here all the way to this surface in gamma 1. We'll subtract this again because we're going up, hence this sign here. And so this will be, from here, it's going to be H1 plus delta H, which is this. And then we find ourselves at this location here, and that has to be P2. So P1 is here, and P2 is here, and this is the expression. So what we have in here, we can now figure out exactly what we can cancel. I guess we have values of unit weight of water 1, unit weight of water 1, and H1. There's a negative sign on them, so we get rid of that. We could take P2 off to the other side if we wanted to and subtract everything off. So that's what we've done here. So we have P2, take it over here. And subtract everything off to the other side. And what are we left with? So we have unit weight of water 2, which is this. We have unit weight of water 1, which is this. And we have delta H here and delta H here. There's a minus sign and a plus sign, and so we're left with this second term here. And so equation 1 is just a simplified expression that defines the differential pressure as a function of the changes in this change in height that we get of this component here, and this magnitude of delta H, which is a small amount here. So the other thing that we can do is we can look at the volume changes in this. So this is this height delta H times, what is it called, by the area of the reservoir, right? If you draw this out. And this fluid that comes from here has to be all squeezed into this particular volume here. So this has to be this area, what they call it here, what have you called it? The area of the tube, multiplied by this height here, which is H over 2. And so the volumes of these, so in other words, if you look at the area of the reservoir times delta H, has to equal the area of the tube multiplied by H over 2. And so that allows us to be able to calculate what delta H is, which is this expression here. And so this, if we substitute in a magnitude for delta H, we end up finding out, being able to define it in terms of the areas of the tube. And so long as the area of the tube is much less than the area of the reservoir, then this term goes to 0. If this term goes to 0, delta H goes to 0, and we don't have to worry about it. If that's the case, then the behavior of this system is purely defined by the pressure difference is just equal to the changes in heights within the tube, this height here, divided by the difference in the unit weights of the fluids. And so if the unit weights of the fluids are close to each other, then this is a small number, and therefore the sensitivity of this instrument to a small change in pressure is quite high. So maybe too much math to be able to make the point, but the point is, if you think about this as a physical system, the easiest way to think about it is just to having a single fluid in it, which happens to be one density. You have a bead in here that starts off, that marks, and a bead in here that marks the location in the manometer where the level is. You change the pressure here, you change the fluid here, this goes down, this bead goes down, this bead goes up, and you can measure the difference in them quite accurately. So it's just a physical construct, if you like, to be able to do that. All right? Okay. And there's some other discussion on that. So, not really something that we'd ask in an exam, I don't think. But this might be one. If you looked at the exams already, which I've implored you to do, and I hope you have, then this would not be an unusual question to have. All right, so what's this? This is a typical manometer question. It looks like bulbs, but really these are pipelines going into the board or into the page, as you prefer. If there's a pressure in here, which is PA, I guess, I'm going to switch back to red just because I can. And so mercury manometer is used to measure the pressure difference in two pipelines. Fuel oil with a given specific weight is flowing in A. So this has fuel oil at some specific unit weight in A, and lube oil is flowing in B. No idea what these are, except for SAE is Society of Automotive Engineers, I think, so they write standards for the viscosities and densities of different lubricants, I suppose. An air pocket is becoming trapped in the lube oil, as indicated. Determine the pressure in pipe B if the pressure in A is 15.3 psi. We won't do any, none of your exams will be in English units. So we know the pressure here is equal to 15.3 psi. So if we want to calculate the pressure B, what do? If you look at the mercury starts here. I don't know how clear that is on the board, and it finishes here. So this is Hg, unit weight of Hg. So what do? We start off at Pa. We go down. How far do we have to go down? We go down to get to this next point, which is going to be 3 inches plus 18 inches. Multiplied by the unit weight of fluid A. I won't do the 12 inches. If it's in PSI, then you need to divide it through by 12, but let's not worry about that. Well, why not? You can do it. This is 12 inches in a foot. We'll find ourselves at this point. If we go down 6 inches in the gauge fluid, this is mercury, multiplied by 6 over 12, we find ourselves at this point. The fluid's simply connected, so we can get to this point. This has to be exactly the same pressure. We go up to this point here, which is subtracting, which is 6 inches plus 18 inches. It's in fluid, which is unit weight B. So we find ourselves at this point. We're in an air bubble, and so we know that the pressure here has to be the same pressure here. And the only way that we can find our way here is by going up 3 inches to get to this point here, and then going down 5 inches to get to this point. So from this point here, if we go up, it's the same as going up in this fluid by, well, it's the same as going down 2 inches, I guess. So it would be adding 5 minus 3 over 12 times the unit weight of B, and that finds us at this point, which is equal to PB. And hopefully that's exactly the same as this. It is exactly the same as this expression. So that's it. So you just have to work your way through the system. What have we used? We've used the fact that on this line here, dP dx equals 0, right? It's just saying that the fluid pressures on a single plane have to be the same. There's no change in pressure. And we used the fact that if you go down in a fluid, you increase pressures. If you go up in a fluid, you decrease pressures. If you move across a gas, then this has to be at the same pressure, and therefore this has to be the same elevation. Okay? So those are basic manometer expressions. All right, same deal. So this question's looking at calculating how much weight do you have to apply in a bag if you want to stop this step from floating away if you're casting concrete in it. And so the step is a form that takes this particular form, and it is an empty box, of course. And inside profile, the box looks like this. The risers, again, are 8 inches tall. Each of these are 8 inches. And the tread, I guess, which is the width of the step, is 10 inches. And so that gives us absolutely the dimensions of this. So 8 inches plus 8 inches plus 8 inches gives us 24 inches. And it's an open form. And so what we can do, what we want to know is how much weight we have to apply on the particular step to keep it anchored down. Because otherwise, when we put concrete in it, you could imagine if the concrete's very dense, it'll just lift it up and float it off its base. There is no base in it. The base is open. And so one thing we do know is that when we fill it up with concrete, then the pressure change with depth is going to be given by this. This is minus z if you like. And so certainly we can calculate what the fluid pressure is at this base. If it's open, the fluid pressure here underneath this height has to be this full fluid pressure here, which is going to be what? 3 times 8 inches times the unit weight of concrete is equal to the pressure PB. If the pressure here is PB here, and we know that if we go to any place along here still in that fluid, the fluid pressure at this point, even though it's only under 8 inches of height, has to be the same. And that's kind of the gist of this question. So the fluid pressure acting along this base has to be equal to, if we draw it out, as we typically will do, a fluid pressure distribution which is equal to individually PB, and the area over which this is applied is this area. It's an area along this dimension here, which is this, but also this dimension here. Right? That's the basal area. So that's one force that's acting. So what we could do is we could do a free body diagram for this. The free body diagram, if we take it around this whole step here, includes all of these 4 components. There's the pressure of the fluid acting upwards. Let me change colors so to be distinct. There's this pressure of the fluid acting upwards, which is on the base, which we've just said we know how to calculate. It's uniform on the base, and it's equal to the total height, the highest height of this, for the reasons that we mentioned. There's the weight of the form, which is the wooden form itself, which you're given, I think, must be 85 pounds, which we know. The weight of the concrete, which we're going to fill it with, and so the weight of the concrete is going to be equal to what? The unit weight of the concrete times the volume of the concrete. And the volume of the concrete is just going to be the volume of this total form. This, if you like, this is V sub C. So we know the geometry of the form. If we know the unit weight of concrete, we have this. And this is what we don't know. We want to know what weight of bag we have to put on this to be able to keep it down. We resolve things in the proper directions. And so if we take downwards as positive, we have the weight of the bag downwards, the weight of the concrete downwards, the weight of the form downwards, and the uplift pressure at the base due to the fluid pressure at the concrete upwards, negative, and they have to sum to 0. Because we know that sum of forces is equal to mass times acceleration. Acceleration is 0 if it's static, and therefore this is equal to 0. So that's Newton's second law. Don't have to worry about forces in y, just in the vertical direction. And I think we probably have everything we need to do that. We can calculate this fluid pressure here. We can calculate the volume in the form. We know the unit weight, so we have the weight of concrete. We know the weight of the form, which is 85 pounds rather. And the only thing we don't know is this. So we can solve for that. And that's done there. I won't go through calculations, but it turns out that you need to add quite a large weight, 655 pounds, which is 3 people, I would say. 3 of me, anyway. to be able to hold that thing down. What would happen if we wanted to make a step that, does everyone get that? What happens if the step we wanted to make was made of a form that had baffles in it? What if the form So this is the form we have now. It has an open hole here, and it's fully open to be able to take concrete all the way through it. What happens if we opened this up, and opened this up, and opened this up, and had a baffle in there? Would the weight of the bag be larger or smaller that you needed to keep it in place? And how would you rationalize it? What's the pressure that we'd have acting up here? This would be PB is equal to, what's it, 8 inches plus 8 inches plus 8 inches, so that's 24 inches times unit weight of concrete. What's the pressure here if there's a baffle? There you go. 16. And by inference, 8. So if you look at this pressure distribution versus this, where this has to be PB is equal to 24 times unit weight. This is 24, 16, 8. By definition, the reduced amount of upward thrust is going to be this area in here, right? So by definition, you should just be able to reason the fact that the weight of the bag that you have to put on there is going to be less. And if the main weight of this, so the only thing that difference is you'd have the same amount of concrete in there, the weight of the form would be the same, and so I guess you could look at the relative, if you take the weight of the form as being negligible compared to the weight of concrete, which I think it is, then you would calculate that how much would you reduce the weight of the bag by? I think you'd almost reduce it by half, right? Because you can draw a line from end to end that would be the integration. So this purple area is probably just 1/2, or it may be 1/3 less than the total. You can do that calculation straight away. Okay? So that's the kinds of things that we'd like to, some insights in this class. I think it's interesting. And of course, the reason for that is that if you have baffles, you can only have the height of fluid acting here that is equal to the height of fluid within each of the baffles. Take the baffles out, then all of a sudden you get this behavior where it's much larger. Of course, it probably wouldn't be a very good step. You take the form off and you just have 3 blocks instead of a coherent step. All right? All right. How are we doing? Are we still alive? I'm not going to do this. This is a really complicated question, so I'm not really sure that I'm in the mood for it, and you might not be in the mood for it either this morning. I'll just kind of give it an outline. So we've talked before, when we talked about individual, and let's just, won't go through the question, but talk about the concepts. We've talked before about the idea that if you look at fluid pressures and how they change with elevation, and if you look at the surface of the ocean, then as you go up in the atmosphere, the fluid pressures will change like this, which are nonlinear. If this is air and this is water. If you go below sea level, then the fluid pressure is equal to P0 plus a height times a unit weight of water. And the reason we've been able to get this is because we've assumed that the unit weight of water is independent of the pressure. So in other words, that implies that the compressibility of water, or the stiffness of water, which you'll remember is equal to a change in pressure either with a change in volume or with a change in density. We've assumed that this density doesn't change as a function of pressure, but it does. If you go 6 kilometers down, which is where this example is trying to do, then there's a very small change in the stiffness, which is given by this expression. So what we could do, if we wanted to, I don't think we will, is we could take our change in pressure with depth term, which is always correct, always absolutely correct, and instead of assuming that the density is constant with depth, we assume that it has a finite compressibility. And this stiffness, rather, which is 1 over compressibility, is about 2 GPa, 2 gigapascals. Very stiff, as stiff as rock, and so it usually doesn't make any difference. But if we wanted to, what we could do is we could rearrange this equation of state, which has a finite modulus and a finite compressibility. The compressibility is 1 over modulus, which is equal to 1 over 2 GPa. And what we could do is we could substitute this value for change in pressure basically into this expression. And if we did that, we'd end up with quite a complicated equation that says that instead of changing the pressure changing as a function of depth as this, then it changes in a slightly different way that includes the compressibility of water. And if you go ahead and work out the pressures at 6 kilometers depth, in one case where it's compressible, you get either compressible or incompressible, you get 61.4 MPa, or in the other case, you get 60.6 MPa. So they differ by something like 2%. Which is the one for the compressible fluid? Lower or higher? Nick, you're the only guy I know here. Lower or higher? Sorry?
Higher.
You got it. Yeah. Of course, right? Have the same mass, it has a higher pressure on it, it's compressed into a smaller volume, so its density is higher. And so if its density is higher, then if you sum up all of those components above you, then the total pressure acting above you on a column of given height is higher because you have some stuff in there that instead of being uniform density, the stuff right at the bottom has a higher density and therefore more weight. And so this has to be the case for where it's compressible. This, because it's less, would be the case where it's not compressible. And actually you can see that right here, I guess. But that's the rationale for it. And they differ by a very small amount. They differ by about 1 MPa in 60, which is about 2%. And so that's why when we do calculations for changes in fluid pressures as a function of depth for fluids, we don't care about compressibility because it's a very small number.